we should be live. I have decided it is better.
Okay.
Yeah. The new system for streaming on YouTube seems better.
Good.
Can confirm. Yeah. That's it. I've spoken.
Excellent.
Did you get that reference yet? No, you haven't watched The Mandalorian yet.
No, I haven't. I've been traveling all week. I'm allowed to be behind on getting yet one more streaming platform.
It's man, I don't know how long I'm going to be subscribed to Disney Plus though. Like I was. So my hope as a Canadian,
Yes.
we don't get access to Hulu Plus.
Right. Which is really frustrating.
Super frustrating. So there is a vast chunk of television that happens that we have no way to access in Canada unless we are willing to pay for cable. And then that just to get a couple of shows like, I don't know, Rick and Morty and things like that. And so in theory, now that Disney owns Hulu, they're going to mash Hulu Plus into the Disney and make it all one big thingy.
Right.
And I don't know if that's what's happening in the US, but
So
not here in Canada yet.
so we're in this weird situation where I can get Hulu with ads with my Spotify. I can get Hulu with ads with my Apple Plus. But I can't get Hulu Plus bundled with one of those, which is
Right.
really frustrating.
Which camera are you looking at? Okay. All right. No
But
problem.
but you're actually slightly to the side of it.
Okay,
I'll
no
stop
problem.
looking at you and look at the camera.
Either way, no,
Sorry.
it's fine. I just want to make sure it wasn't the completely wrong camera.
No, I was also while we were chit-chatting, looking at a chair on the internet.
Oh, perfect. Please, no, please keep shopping.
Sorry. We are streaming now, aren't we?
Yeah, we are. You know.
Okay, I will stop doing that.
No. I think you can multitask. Gigantic brain. You can do it all at the same time.
Yes.
Yeah,
But
and
eye
so
contact.
I looked through Disney Plus, and the problem is that I'm sure this is a situation for a lot of people. We've seen it all. And so, right? Like, yeah, I've seen all the Avengers movies. I've seen all the Marvel movies. I've seen all the Disney movies. I've seen it all. And so
Right.
what had I not seen? I had not seen Captain Marvel, so I watched that. Yeah, it was fine.
Yeah.
And there's a couple of new shorts they put on, and of course there's this thing with The Mandalorian.
Right.
And so we watched the first episode of The Mandalorian. It was fine. It was, I mean, if there was Star Wars bingo, I would have won it because it was just like every single Star Wars trope you can expect was in there, no question. But I can't imagine me hanging on to it for one more month. And the only saving grace is that my kids will. I say kid because one, like, Logan, he doesn't care. He plays video
Yeah.
games. He doesn't watch that kind of stuff. Chloe has a lot of nostalgic shows that she still wants to watch.
Right.
Gravity Falls and other stuff that's available, Disney movies, and I think that she'll even get on the other side of that nostalgia and then won't need it. But I
Yeah.
think for most kids, like if you've got young kids, this is going to be so valuable because they could
Right.
just wear out the internet watching these things episode after episode. And 10 years ago, I would have been all over this and I would have just like, as opposed to running around and buying DVDs and taking these out from the
Right.
library, kids just would have watched it. But at this time in my life, I don't even how many 500 things on there and there's nothing to watch.
I do admit that I want to go back and watch some of the shows that I liked as children to verify how well they didn't age. Like I remember there was this one Disney Presents movie that was like a cat that was an alien and they had to get it to the top of a mountain or
Mm-hmm.
something, and
Yep.
there were two children
Yeah,
that
I
were
remember that. Yep.
aliens. It was like
Something,
Terabithia Mountain.
something mountain. Yeah, I remember that.
Escape to Witch Mountain,
There you
that's what
go.
it was. So I want to go back and watch that. And there was this other show that I can remember almost nothing about, except that it was filmed in the Sequoia National Park, and there were little tiny gnome-like creatures that lived in Sequoia National Park and were becoming endangered, and they're like going along with this family that picked them up in their car trying to save their peoples. And like I just want to figure out what was the rest of that movie that I'm incapable of remembering.
Right.
And I know it
Okay.
was Disney.
Yeah, the Brian Yuku is asking if the Navigator movie is. That is, yep. Flight of the Navigator is on there. I went through the whole list, everything, to see if there's anything I wanted to watch, and I just came back with like they've got some documentary about rock climbing. That's kind of cool. I'll watch that.
Okay.
A couple of National Geographic things, and then I'm gonna cancel because
Yeah.
there's nothing I want to see on it until they come back around and they implement Hulu Plus. Then I'm in for the long term.
Right.
I'm going to say hi to, we missed the 5-minute window, but Brian Yuku,
Oh, no.
Cherry Catnaps, Esquilax, Frank Tippin, Janelle Duncan, Jordan Albert, Kevin N., Linda Sedik, Michael Bonnet, Orbit Over Luna, Rich Wilson, Susie Murph, Therion, Zappan. I started the stream and then everybody else's hellos all disappeared. I apologize. But then I got the people who normally we don't say, so I feel like it's a good balance kind of thing.
Yay. Go
Yay. Go team. Anything interesting happening?
I got a grant submitted today.
A grant submitted. Not a grant won, but a grant submitted.
No. But when you have to submit 55 papers that conform to rules and regulations, getting it submitted is a pretty big win. And when you know that there's only a 1 in 8 award rate,
Yeah.
I won by submitting. Here's to hoping. I think it's a good grant. I'm proud of what we created as a team, but I fully recognize probabilities are always low. But I got it in.
Yeah, but you have a higher hit rate than most.
I do, but the past 3 years has been rather rough, and I haven't published any papers during that time. So one of the things that academia is utterly unforgiving about is if you do have a rough patch, they just don't let you come back necessarily. So here's to hoping that it's enough to say, here's the awesome things that we want to do, here's how we'll do it, and that they don't go, yeah, we agree, this is awesome, but you're the wrong person.
Yeah. So I've got a bunch of really interesting open spaces coming up, which is on my YouTube channel that I just want to mention. On Monday, we've got Paul Geithner from James Webb Space Telescope. He's actually from Northrop Grumman, but he's an engineer working on that. So we will talk about that, and that hopefully will correspond to an enormous episode that we're working on all about James Webb. You don't want to talk about satellites that haven't launched? I do. So it's going to be big. Like it's easily going to cross the 20 minute mark, I'm sure. After that, I've got a NASA engineer named Casey Hanmer, who is really interesting sort of philosophical and thoughts about the future of spaceflight, what SpaceX means to spaceflight. Really interesting guy. I'm really looking forward to talking to him. Man, they just go on. I've got one of the heads of NASA's NASA Innovative Advanced Concepts, NIAC. So one of the people from NIAC coming to talk about that. People from the Ariel mission coming. So for the people who got used to me just showing up without a guest, those days are over. We've got at least a month plus of really cool guests. So stay tuned.
That is awesome.
If you're wondering what it is that you've stumbled into, this is an episode of Astronomy Cast. I'm Fraser. That's Pamela. We're going to take the next 25-ish minutes, and we are going to record an episode of Astronomy Cast. And you're going to watch. I should get my recording software ready.
I have a dog licking my table.
John Suffill says, all these worlds are yours except Nibiru. Attempt no conspiracies there.
I I like
That
that.
is
Can we please?
awesome.
You need to make a shirt of that you can post up on Redbubble so that I can buy it.
There you go. Let me know when you're ready.
I believe that I'm ready. Hopefully Audition won't yell at me this time.
Say when.
It's going to make me give it a name. What's our number this week?
547.
Okay. It has detected a problem. The default input device appears connected but is not responding. Well, F you too. Why do you say it's not responding? I see it. It is there. It has strong opinions.
Yeah. In
Okay.
other news, while we're hanging out here, played around with the telescope some more. The observatory from OPT. Man, it is so cool. So fast.
Did you get to see any of the Mercury transit?
No,
But
we
did
were
you
totally
try?
clouded out.
Okay.
Yeah. I looked at the pictures from space.
That works.
Yeah.
I'm going to try recording again. It is recording.
Oh, good. I'll also press record. And it's
Yay.
working. Here we go. Astronomy Cast episode. Wait. Okay. All right. The numbers are wrong. Okay. Let me just fix this before I mess this up. All right.
We love you, Susie.
Astronomy Cast episode 547. Why astronomy still needs humans. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Great. Back from more travels.
I am. Last week, I was out in San Francisco for QCon, and I'm so grateful for the opportunity to attend that the hosts gave me. It was an amazing week. I feel so inspired. All I want to do is go and write software. Unfortunately, I have paperwork I need to get completed first, and then I'm going to write all the software. All of it. All of it will be written, and I will enjoy it.
I booked flights for me and Chad to attend the American Astronomical Society meeting in Oahu in January. So
Excellent.
We're in. We'll be there. And so if you're listening to this and you are also attending AAS, find us. Let's hang out.
We will all be there together.
We'll all be there together. Yeah. Few sciences have been able to take advantage of the power of computers like astronomy. But with all this computing power, you might be surprised to learn how important a role humans still play in all this science. Pamela, you're telling me that humans haven't been completely relegated to the feeding and servicing of computers?
There are days when we think that would be
When
the
you
best of
feel
all
like that?
possible options. But not yet. They still need us. It turns out there's still stuff that machine learning and computer vision just can't quite do.
Yeah.
And we're needed. We're actually needed.
But it is surprising. I mean, this episode is going to be about how humans are still needed, but it is pretty amazing how much of modern astronomy is completely due to and thanks to the power of computers and modern. I mean, when you think about what astronomers had to go through 100 years ago when they had to take pictures, they had to, on photographic plates, they had to blink back and forth between those photographic plates to try and find things like Pluto. Oh, the work. And now, beep boop, computers do it all for you.
And what's really amazing, just to give an example at the beginning of this, of the extreme opposite case with the Gaia data sets, there are people who have pre-written possible papers such that when the new databases of data get downloaded, their software crunches and then outputs the appropriate blocks of text for what was found in the database, and then submits the paper so that people can essentially beat one another to publication. And this auto generation Mad Lib style research era that we're now in is truly amazing. But then at the opposite end of that, we have the science we're talking about today, which is where you still have researchers gathering around a table with a Wacom tablet and screen, hand drawing things on images, trying to figure out what it is they're looking at.
So what are the places then where human beings still have a role to play in the science of astronomy?
So we have four basic roles that we're going to hit on during this episode. The first is we're there to confirm that the computers didn't go off the rails. So we're there
Right.
to essentially look at the potential supernovas and say, yes, that actually is a supernova and not a cosmic ray. We are there to
So sorry. So just give like that as a specific example, right?
right.
How would computers be involved in trying to find potential supernova candidates? And then how would a computer go horribly, horribly wrong in attempting to identify this and where a human would be called in? So what's the process so people can understand?
With supernova in particular, and this works for a lot of different things, you can do a similar process with asteroids, for instance. You take two images of the exact same area of the sky. You then subtract these two images, and where nothing moved and nothing changed in brightness, you should get nothing. Nothing is a good result. Now, the reality is that from one night to the next, sky conditions will change. Stars will appear a little bit fuzzier, a little less fuzzier. And what you actually end up with is residual donuts. And if you have an object that is significantly brighter in one image, or is present in one image and not present in the other, you will end up with a brighter spot and a darker spot in the two partner images. Now, that's if something's moving. So you have it moves, it ends up subtracted out in one image and added into the other image. If something stays constant, you end up with sky brightness. If it just brightens, you end up with it in one image and it's there. You have hopefully a supernova. Now, the problem is that brightening doesn't actually have to necessarily be the star that did the brightening. You can end up with annoying things like a cosmic ray that coincidentally hit it exactly where your star is. You could, or in this case, where a fuzz of light in a distant galaxy is.
And a cosmic ray is a blast of essentially light on the detector. I mean, the detector sees it as this place where something was very bright. And when you make that subtraction of the two images, you're going to see this bright object that's there when really it wasn't a supernova exploding.
Right. Exactly. You can also get weird things happening with your software if a satellite crosses in the wrong place, wrong part of your image so that it's coincident with something. And human beings need to be there to do the, that was a really weird supernova, or not supernova, that was a really weird cosmic ray. Our software can't handle it. There was a coincident with, sorry, Susie. There was a coincident satellite shoot. Our software couldn't quite remove it. All these little things end up with false positives and sometimes false negatives, which are way worse when something real happened and your software is like, nope, I'm going to ignore that. So human beings have to constantly be in there monitoring the things that change that the software flags to go, yes, that's real. No, that's not.
The false, I mean, you mentioned this, the false negative problem. That is scary. Mm-hmm. That you are trusting a computer to hammer through 100,000 photographs that have been taken of the sky, looking for differences and there might be a supernova in there. And for whatever you have defined the characteristics of your software, it's going to go, nope, not good enough. And it's gone. And you're
And
not going to
it's
double check 100,000, right?
no, and in terms of supernova, it's annoying, but it's not actually scary. Where it actually is scary is in the sky surveys that are out there looking for the asteroid that's going to hit the planet Earth.
Yes.
And the most dangerous ones are the ones that we get very little warning on, the ones that are coming at us out of the direction on the sky that corresponds to the sun. And we might not get a lot of warning. So you don't want those to be ignored by your software.
There was a really dramatic example of it just this summer. There was a one of the closest calls that Earth has had in a long time, and it did get picked up in the automated sky surveys, but it also happened to be a time when I think there was like a full moon nearby. And
Mm-hmm.
so the full moon matched with the direction that the asteroid was coming from, matched with the small amount of time that they had to find it. They, they missed it.
Yeah.
And then it went
And
right past the Earth, and everyone was like, "What?"
yes. So, yeah, the sky is a dangerous thing sometimes. It throws rocks at us.
Yeah. So this is one classification that you were mentioning. What else is there?
So beyond being there to basically check is the software off its rocker, there's also going to be a lot of times, and this comes up more in astronomy than it does in planetary science, where we can train our software now to go through and say, this is a potential, this kind of thing, this is a potential, this kind of thing. And it does this via machine learning, where you can take an image. And one of the things that doesn't require machine learning that we've been able to do for my entire career is go through an image and find every source of light in the image, identify where all the stars are, find those disparate globularly things. And we're finally at the point now where machine learning can go galaxy, galaxy, planetary nebula, maybe, but there's a lot of weird looking stuff out there, especially the hydrogen emission regions, those beautiful red nebula that we love to look at, supernova remnants. These things all like to come in entirely their own shape. Even many planetary nebula aren't that nice classic round shape. They take on their own structures. So what the software can do is, there's something here. Look, please look. And we have to essentially go that next step for our software and say, aha, yes, thank you, software. Let me tell you what this is. And that's still kind of awesome that the universe has certain classes of objects that we haven't seen so many times that we can train our machine learning yet. Now, when it comes to the future of the Large Synoptic Survey Telescope, we will hopefully begin to get enough data that it turns out that all those square planetary nebula are old school and we can just let the software do it, but we're
Right.
not there yet.
So again, like provide me with an example of what that feels like as a professional astronomer. The How do you know that thing is a nebula or it's not if the computer can't tell? The computer has again gone through the 100,000 images. It's spat out all the weird stuff, and then you look at the picture. What clues would you use as an astronomer to figure out what this thing is?
Well, quite often the machine learning isn't smart enough to generalize between a bunch of different things. So when it keys in on trying to identify what a thing is, it may look at what is the distribution of light in the image. That I know of, we don't yet have anything that's smart enough to use multiple catalogs to be able to cross correlate. But I, as an astronomer, can go, this dead bug shaped blob of stars and gas in multiple different colors. This is a star forming region. This large field of red light that has large swaths of blackness through it. This is a hydrogen cloud with dark, dusty bands in front of it. And this is because my brain has the ability to key in on all the individual features and understand that this set of
Right.
things,
Right.
this is what star forming regions look like. This sort of thing, this is what hydrogen gas emission areas look like.
Right. And so
We
it's
can
like you're
see things.
putting the thing that you see in context of the larger structure that you're looking at the same time, and human beings are very good at that.
And we don't care what kind of dead bug a star forming region looks like. We're able to interpolate across all these possible different shapes on the sky and say all of these things that, yeah, they all have different boundaries, they all have different patterns of light and dark. These are actually all the exact same thing.
Right. What else?
Well, over in planetary science, I we have the surfaces of worlds, and it turns out that software and the surfaces of worlds do not get along. We are to the point that some of the best algorithms out there are doing better than 90% in mapping out simple things like sharp boundary edged craters when the training set and the area the software is doing is the same kind of surface. So you're sticking to the same kind of regolith, you're sticking to the same kind of mare on the moon, and you're not doing anything crazy. But 90%, 95% even isn't good enough if you're trying to land a spacecraft because let's face it, the moon and Mars already like to eat spacecraft when we know exactly what we're doing. Let's give our little rovers and landers every possible chance they can have, and well, to do that, human beings need to be mapping these landing areas. And this gives us a job. We have to fill in for what machine learning isn't clever enough to do yet, even with these objects that occur millions of times on a given surface. So, all those boulders on Bennu,
Right.
that's on us.
Yeah.
That's on us.
Now, is part of that though, like there's a photograph of, say, the surface of Bennu is a good example, right? And of course,
Yes.
you're maybe all you dream is Bennu at this point with the amount of rocks that you've identified on the surface of that collection of rocks. But is part of it though just the quality of the data that you have so far? Like if you had an aircraft on Mars that flew over a potential landing zone very carefully with a laser altimeter to measure a 3D construction of every single object, that would be easier to feed into a machine learning program than one photograph taken from orbit around Mars. It's those first images where it's vague, and so the human really plays a role when later on, once the science or once the data gets better, then the machines can step in and figure this out with more accuracy.
I wish it was that simple. What we're running into with the Mars and Moon is we have LiDAR data of both of these surfaces, but the LiDAR data isn't of sufficient resolution. And there's enough scatter and noise in it that it doesn't get us down to being able to see the same kinds of details that we can see with the cameras. High rise on Mars Reconnaissance Orbiter, the narrow angle camera on Lunar Reconnaissance Orbiter, these are recording things at amazing resolutions. With the moon, we're down at tens of centimeters per pixel with the highest quality images. And this means that if you were to lay down on the moon and assume the snow angel position, we could see you on the moon. And with these resolutions, we should be able to just say, go forth, software, and at least tell me everything that's 10 meters and bigger. What we run into is there are issues of the sun has this super annoying habit of moving through the sky and the shadows change. Okay, fine, we can deal with that. Well, soil comes in different colors and textures. Well, software can't generalize across that. And then you just have weird stuff. So on the moon, you run into things where we have these magnetic anomalies that cause different grains of material that are radically different color to land in these patterns that look like, well, somebody's been sand painting swirls on
Yeah.
the moon. And how do you get your software to understand that A crater in one area of soil is going to be filled with white and spray white material everywhere. A crater somewhere else is going to be black on the inside and spray black material everywhere. Sometimes it's a little of both. Sometimes it's gray all over. Sometimes you're going to have patterns of color that have nothing to do with topography. And as the sun moves, everything changes.
Right. And so, in theory, you could take over a whole bunch of really powerful computers, feed them lots and lots of examples, and teach them carefully to learn how to identify these things. But maybe the quickest thing is to have a human being take a quick look. Teach a
And
4-year-old to identify craters on the moon or rocks on
they don't.
Bennu.
So the
And
4-year-old doesn't have the physical hand-eye coordination. Go 4-year-old. I love you. You
fine,
can't do
and a
this yet.
10-year-old, you know.
Yeah,
Yeah.
fine. That
Yeah.
yes. And the other problem that we run into is especially for objects like Bennu, which is a half kilometer across, you could sit it down on a large city block. It's so tiny that we could try and train a machine algorithm, but the data set would be the entire surface of Bennu. And if you have to train your software with your entire data set, you've now written software that has no purpose. So with the moon, what I'm really hoping is we'll figure out a sampling set such that if we hand mark 10% of this kind of geology, it will be able to go off and handle the rest. But we're still going to have to do 10% of every different kind of surface combination of color, texture, sun angle. We're not there yet. And it's super frustrating to not be there yet.
Right. When the kind of science that you're trying to do is like, where's every crater on the moon? And then let's figure out how old different parts of the moon are. Or where's every rock on Bennu so that we can figure out which is the safest place to land? Or where's every potential Kuiper Belt object that New Horizons could visit, et cetera, et cetera. Like, you're like, with all of this, it's beyond just like, I want to find a specific example of a thing, and it's moving to, I want to understand it all so that I can make some larger just understandings about what's going on.
It's super annoying.
So
We
what
have
was the
humans.
what was the fourth one?
So then the fourth one is the things that we can't even begin to tell computers how to do. And this is actually what inspired me to do this entire podcast. A couple weeks ago, the New Horizons team released detailed geologic maps of the far side of Pluto. What we have come to do is the near side is the side that was nearest the New Horizons spacecraft when it did its closest approach. The far side is the side that we've only seen in the lower resolution data that was taken when the spacecraft was further away.
Like the moon, it has no dark side.
Exactly. And looking at these maps, they're super cool. And they have these beautiful curved continuous edges going from one geologic feature to another geologic feature. They trace out all of these different stripy bits, light planes, craters, and all of it was hand drawn. All of this is science that's generated most often by people sitting around a Wacom tablet at a table and staring at a monitor together, and as a group deciding this line should go over here. No, let's shift it a pixel, let's erase that and extend this a bit. And this unification of art and geology as the only way to get at geologic feature maps is something that I find absolutely remarkable, truly beautiful to look at, and super frustrating because it means there's no clear mathematical definition of what belongs to Sputnik Planum and what belongs to the stuff beside it.
And so those maps, and I think we reported on that on Universe Today as well, that it got images of Pluto when of the other side of Pluto when it was so far away, and it was just this teeny tiny dot. And so it's amazing, right? You've got these astronomers that are sitting there and free form attempting to draw what they see.
And
Large impact craters, more regions that connect to Sputnik Planum, etc. It's quite an amazing piece of work.
and they get really good results where it's all by eye. It's the human mind can look at Pluto and say, based on the shadow, the texture, and the color that I see here, these are mountains. And then combining spectral information, these are water mountains. They can look at the color variation across Sputnik Planum and see where there's been convective cells that have changed the surface ever so slightly from one point to another. And this is all subtle variations that are specific world to world, specific place to place. And these are things that, because machine learning can only do what it's been told and what it's seen examples of, every new world is going to have to be done at this point in our technological evolution by individual scientists working by hand.
I love this idea that they had these images of Pluto. I mean, we even had images of Pluto from the Hubble Space Telescope, and I've even seen people do that. They've gone back now and recreated what Hubble was seeing now that we know what it
Yes.
actually looks like. And so we got the close-up images, high resolution, and then in turn a human can interpret what that looked like and look at low resolution images and do a better job of showing what's there. And then you can take an even lower resolution and do a better job of figuring out what that is. And probably if you have more distant, and then you compare what was seen with, oh, and I forget the name now, our MU69 Ararock, I forget the way
Yeah.
to say it. You've got different surface features on that, and now with two different versions you could show someone a low resolution image of a third object, and people could take a crack at attempting to see what's on the surface, map out the surface features of that world without necessarily having to get as close as New Horizons did. So it's a very powerful process, and as you say, couldn't be done without humans. I love those old sketches that people used to do of the moon and Jupiter and galaxies and
Mars.
things, Mars and things like that. I mean, okay, so maybe some of them thought they saw canals, but I, most of the time they're absolutely fascinating. And there's a lot of astronomers, amateur astronomers, and even professional astronomers that still sketch to
Yes.
help understand what they're looking at.
And there's psychological research that shows that the connection when you're physically writing and drawing is significantly greater than when you're pounding away on a keyboard. I don't fully understand. I just know that this is what the research is showing. And it's getting to the point, however, with all of our devices that allow styluses to be used, especially with the Apple Pencil, you can bring all of that hand eye cognition into what we're doing with our scientific images. And what I'm also really loving along these lines is seeing people then repeat the cycle as they're hand drawing their notes, listening to conference talks, so that you're going from digital image off a spacecraft, scientists around a table drawing the map, scientists listening to the talk, recreating the drawing in their notebooks. And art is really at the core of planetary science. And this is something I would never have guessed at when I was a graduate student.
So I think we still would both agree that learning to be a computer programmer is one of the most valuable skills that you'll be for
Yes,
becoming an astronomer. And yet, don't throw away your drawing pencils as well.
exactly.
Thanks, Pamela. Do you have some names to read out this week?
I do. As always, our show would not be possible without the generous contributions of folks over on patreon.com/astronomycast. You keep our show going. You pay Susie. You're going to be helping out with our AAS travel. So thank you to Frederick Hagnik vom Jensen. Thank you to Philip Walker, to Elad Avron, to Cooper, to Chris Schauerhofer. Sorry about that, Chris. Thank you to Paul Disney. Thank you to Dave Lackey. Thank you to G4 184. Thank you to Stephen Ludking. Thank you to Sarah Turnbull. Thank you to Dana Nori. All of you are our heroes this week, and we'll have new heroes next week.
Right on. Thanks, Pamela. We'll see you next week.
Bye-bye.
Don't go anywhere.
This is where we save. So that noise in the background is the dogs deciding they need to be elsewhere. And the irony is I've learned to leave the door open just a small bit. And I had a door stopper in there, except they kept chewing up the door stopper. So I now have a dog bone that they abandoned holding the door open. So if I use a dog bone as a door stopper, it works. If I use a door stopper, they chew it up. This is my life now.
This is your life.
So thank you to everyone over on Twitch. Thank you to everyone live on YouTube. If you want to join the single community that rules them all, it's the one that's down below us, the Weekly Space Hangout over on Slack. Check out weeklyspacehangout.org.
You go to wshcrew.space. Yeah.
Yes.
Okay, and now is the chance for you to hit us with your questions. James Aberson asks, is ISS affected by debris that causes meteor showers?
Only insofar as it occasionally gets struck with micrometeors, but that's like an ongoing issue, and there's really not significantly more danger during meteor showers like we're having right now.
Yeah, there are. When the space shuttle returned from space, the windscreen was like mildly sandblasted.
Yeah.
And there's tons of little impacts all through it, and they fix it after every one. And there are solar panels that have been hit by micrometeorites. It's just part of doing the job, but nothing is like, it's not like during a meteor shower they're more extreme.
John, you're confusing me in WSH crew, but I'll take it.
Esquilax asks, is a sun-synchronous orbit possible around the moon, or does it rotate too slowly for that?
I'm pretty sure it rotates way too slowly for that. But what is possible is to simply take images over and over until you're able over time to build up a catalog of things under uniform lighting conditions. And I think they're getting pretty close to that, or they've already done it.
So can you explain what a sun-synchronous orbit is and why it's so important?
So here on Earth, it's something that's relatively easy to do because we're a much bigger planet. Sun synchronous orbits are orbits that go over the poles of the planet and go around the world such they're always looking down with the sun at the same angle relative to the surface of the planet. So you may be looking at different parts of the planet below you, but the shadow length is always the same.
Right.
And this is especially useful for spy satellites where you're trying to see things change.
And so if you were trying to orbit around the moon, you'd need to go very, very slowly. You'd need to take 28 days to go, I guess, for the moon to rotate under your spacecraft while you're just going over and over and over. Another place to get a sun-synchronous orbit is to go to the Sun-Earth L1 Lagrange point. Yeah. Then from that point, you are hovering at a point where you're always looking at daytime on Earth. And that's what the Discover satellite was doing.
Cruddy resolution of the moon if you try and do that.
Yeah. But you're farther away. So that's another way to get at that. Larry Beckham asks, is software looking for green pea galaxies?
I don't know yet. I know that they went through at least the Sloan Digital Sky Survey and did it all by eyeball. I don't know if they're going to be trying with the Dark Energy Survey, which is the next big survey, to take on what has been done with Slim Digital Sky Survey and replicate it using software.
Is that the next big survey? I mean, there are
Yeah.
big deep field surveys coming after Sloan Digital. Well, LSST, I don't know if LSST is going to go quite as deep as Sloan Digital or the follow on one, but it's
No, no, no. It goes way, way deeper than Sloan.
oh, it does. Okay,
Yeah,
and
it goes way deeper
every
than
3
Sloan.
days or whatever, it does the whole
Right.
sky. Or it
No,
does the whole sky
this
that
is
it
why
can see.
LSST is traumatizing. But the Dark Energy
Traumatizing.
Survey
I
has
love that.
already started, so it's next, and then LSST, when it starts to
Yeah.
function, it's going to destroy all of us. Um, yeah,
Orbit.
they're.
Oh, go ahead. Yeah.
I was just going to say they're looking at 15.4. I think 15 point. They're looking at more than 15 terabytes of data per night.
Yeah. Do you remember what the limiting magnitude of LSST is going to be?
It's over 20. I don't
Yeah.
remember what over
Yeah.
20.
Ridiculous.
Yeah.
Orbit Over Luna asks, have you done an episode on the science of Lagrange points? Yes, we have
A
done an
million years ago.
yeah, we did do an episode on Lagrange points, and I also did a 3-part series, video series on Lagrange points over just a couple of weeks ago on my YouTube channel. So if you want to see that, I did one episode on L1, one episode on L2 and L3, and then another episode on L4 and L5. So I feel pretty confident that if you've got a question about Lagrange points, it has been answered in either here in Astronomy Cast or over on my YouTube channel.
Yeah,
Pon-
and I see
Go ahead.
I see that Drop Bear Addicts is asking what is the resolution of the lidar on Moon and Mars. Mars is 5 meters. I'm pretty sure the Moon is a little smaller than that, but still multiple meters.
For LiDAR.
Yeah, so
And
this
that's
is for
worse
lidar.
than the visual observations, because the visual observations made by, say, I spit my tongue, Mars Reconnaissance Orbiter and Lunar Reconnaissance Orbiter is around a meter. So
Well, it's tens of centimeters
yeah,
for LRO.
yeah,
So yeah, the laser resolution is significantly less.
yeah. Ponder asks, what's the difference between the event horizon of a black hole and the event horizon of a wormhole with regards to time dilation and spaghettification?
Uh, White holes don't exist.
Was it white hole or wormhole?
Um, Sorry, wormholes don't
Yeah,
exist. Both
yeah,
cases are
yeah,
true.
yeah.
Both cases are true.
Well, you don't
Um,
know. You don't know for sure.
by definition, they can't exist because they collapse something. They collapse the second something falls into them, and cosmic microwave background.
So, um, is everywhere at all places. But I guess but if they did exist,
If
would
they
you
did
experience the
exist,
same kind of time dilation and you're not going to get that time dilation and
mm-mm.
spaghettification you get with a black hole.
I don't know about. I don't know for certain, but
Right.
I don't think so. I'd have to look it up. I have to admit my understanding stopped with, and they collapse the second energy enters them.
Right. That they are an interesting mathematical concept defined by Einstein and Rosen, but practically probably don't exist. There was an
Yeah.
interesting piece of research that came out a couple of weeks ago where people were thinking that there could be a way to see if there is a wormhole at, like, say, orbiting around the supermassive black hole at the middle of the galaxy, just by the way light would be moving through the wormhole could make it cause like a weird flare as it orbits around and we see down the throat from our perspective. But still, Therion asks, any thoughts for all mankind? Have you seen that yet?
Not
That's on
yet.
Apple. You probably would be allowed to because you are an Apple fanatic.
Right, but it's a free 1 month trial that I decided to wait to start until I was done traveling.
Right, right. No, but if you bought an Apple phone or device recently-ish, like within the last year, I think you get a free year of it.
Oh,
Yeah.
okay. I only saw free 1 month,
Well,
so
maybe
I
that. I
haven't
mean, maybe they
started
are
my one
doing the
month
math
yet.
and calculating what you deserve. So Um, Ben Kalo asks, I've heard that lower mass rocket fuel is preferable because the exhaust speed is higher, like ion engines. But given Newton's third law, why is lighter and faster better than heavier and slower?
The problem with so much of what we do is this horrible reality that force equals mass times acceleration. And so the amount of acceleration you get goes down if your mass goes up. And so if you're carrying a bunch of heavyweight fuel with you, you just can't accelerate yourself as effectively. If you're carrying a whole bunch of low weight fuel with you, well, you're going to accelerate more slowly, but you don't have as much mass to fight against. So it's more efficient in the long run.
But is it, I mean, I know that the exhaust velocity that you are throwing things out the back of your spacecraft matters a lot.
Yes.
So does the is it the mass of the particles that you're throwing out the back? In this case, they could be exhaust gases, or is it the velocity? Which one of those makes the bigger factor, or does it not really matter? Like it's just
It's conservation of momentum. So it's mass times velocity. So you can get the exact same thrust given proper technology, which we don't necessarily have for ion drives, out of both kinds of drives. So smaller mass times much larger velocity versus larger mass times lower velocity can give you the exact same change in momentum of your spacecraft. Now, MV out one side is going to be equal to MV out the other. So the amount that you can change your spacecraft's velocity is also directly related to its mass.
right.
So the larger the mass of your spacecraft, the less you can change its velocity for the same amount of momentum getting lost out the back end.
Right. And so when you've got a chemical rocket, you've got, in many cases, multiple tons of fuel on board your spacecraft, and you are throwing them out at a, uh, you know, one velocity. I forget the exact velocity that a chemical rocket is going to be firing at. While, say, an ion engine, one advantage is that you're using electricity, using power from the sun to run the electricity to then
Right.
accelerate these ions out the back of the engine. So you don't need to carry oxidizer in the same way that you do with a chemical rocket, which already decreases the amount. And also, you are accelerating these ions out the back of the spacecraft at a vastly higher velocity. And so you're able to get by with hundreds of kilograms of fuel on board your spacecraft as opposed to many, many tons. And so the total mass of your spacecraft with its fuel is a fraction of what it would be for a chemical rocket. So
And there's less chance of the whole thing exploding, which I find comforting.
yeah, ion engines are wonderful. I really
Yeah.
like them. And at this point, they have been demonstrated for so long and in many missions that they have a welcome spot in almost any mission that anyone's
And
trying to do.
and we should congratulate the folks with Hayabusa 2 for successfully departing at like 10 centimeters a second from Ryugu using their ion drive. And it's just one more case of go team. Asteroids are the place to be using ion drives. TIE fighters, not so much.
Yeah. Well, you never know. NASA actually just this week tested out a new, their next generation ion drive. They tested it in one of their big vacuum chambers at Glenn, and these solar electric
Mhm.
ion engines that should have a lot more thrust. Like they may have as high as like 1 whole Newton of thrust, right? But could be used for future missions to Mars. A lot of really interesting ideas. Station keeping on the Deep Space Gateway.
Yeah.
A lot of cool ideas.
In my fantasy world, we gift the next generation of astronomers by launching an ion drive something to Neptune
Mm.
or Uranus.
Yeah.
Because that's slow and steady with less delta V change is the best way to get there, but it's not going to happen in time for my lifetime.
Yeah. Um, all the Starlinks use a krypton ion thruster.
Those are a different issue.
What, krypton as opposed to xenon?
No. Just the Starlinks. They're something that you want to be able to get out of your way a little bit more quickly than they can.
Yeah, apparently this latest batch, they made them fully disposable. So, but when they crash back into the atmosphere, they come apart in exactly the right way to get them to fully burn up. So, which makes you wonder, the previous batch wasn't?
Yeah.
The other 60
Yeah,
wouldn't?
that's a bad thing.
Yeah. So, good that they are. And I mean, they're relatively small, and they will almost certainly completely burn up when they come through the atmosphere. But I guess in that first batch, some chunks won't entirely. Anyway.
That's like almost compostable.
Yeah, almost compostable. But it's the kind of thinking that goes into, say, the way a car gets into an accident. And now, the old cars, your engine block would just run right through the passenger compartment, and people would die. And now the whole car crunches and crumples in a way to maximize the safety of the people on board. And hopefully they've as well modified the amount of light pollution that they're going to generate. So I haven't heard, I mean, this new batch, you can see the new batch flying in space right now, but as you could with the previous batch, but eventually they'll move to a higher orbit and they'll become invisible as well to the naked eye, but definitely visible to telescopes. Fish RSA asks, has the EM drive concept completely faded away?
I think there's still some projects funded, but they're not anyone's highest hope.
Yeah. I mean, the last that I'd heard, there was a great group in Germany that was doing some really careful tests of the EM drive and the Mach drive and all these various propellantless, violate the laws of physics kind of drives, and each one seems to have an explanation that they're interacting with the Earth's magnetic field in some way. So you're probably, like if you can make a spacecraft do this, then you get to, on the one hand, have a way of traveling quickly in space, and on the other hand, you need to overturn physics as we understand them. So
Right.
That's a tall order.
That's hard.
Yeah. Let's see. Were there any more questions? We're sort of reaching the end of our hour anyway, so we might as well wrap this up. Thank you, everybody, for joining us and watching the entire thing live. You're maniacs, but we appreciate having you join us. Thanks to the moderators. Thanks to our editor/producer, Susie Murph, for fighting her way through the garbled audio that we're going to be supplying her at the end of this episode. We couldn't do this without you. Thanks to all the patrons. We will be right here again next week, unless there's some kind of travel.
No, next week we're going to do a double header, actually.
Oh, we will.
Because
okay.
The week after is American Thanksgiving, and I'm doing Friendsgiving.
Perfect. All right. So we'll see all of you next week.
Bye-bye.
Press the button. I don't know how to stop this. Oh, here we go. There's the button. All right. See you later. The new interface.